Thanks everybody for showing up on this Wednesday evening. My name is Chiradeep Vittal. I work for Citrix Systems. What I do at Citrix is I work in the networking team, and I just joined the networking team from a different gig. I used to work in the cloud team where I was acquired into Citrix after we built this AWS clone called Apache Cloud Stack. I still contribute to Apache Cloud Stack, but the important point is that when I was at Apache Cloud Stack, I was working on the cloud and I was building orchestrators. And so when I moved to the networking team, my job was to help Citrix customers move to the cloud, specifically the public cloud, and also adapt the Citrix products, the networking products, to be more friendly for developers and DevOps. The overview of my talk is going to be, I'm going to give you some background, what is Citrix, what is Netscaler. I'm going to assume a lot of AWS knowledge, unfortunately, and I hope that's okay. The goals for my project, the approach that we took using AWS Lambda, and some of the learnings that we got from developing this project. So Netscaler is a load balancer, and I hope most people here know what a load balancer is. This is, if you have used Amazon ELB, you should know what a load balancer is. And it's a software piece of software, but it's also available in different form factors. So you could buy it as hardware, you could buy it as a virtual machine, you could buy it as a container. And it powers some of the biggest web properties in the world. And chances are, if you bought something today, it's read a news site, your traffic has gone through a Netscaler box. And the magic is entirely in the software, so we get these humongous speeds like 120 gigabits per second and 75 gigabits per second of SSL throughput purely through software. So it's a finely tuned beast, and that led to a little bit of difficulties. And with the load balancer, you can spray traffic to a set of backend web instances. You can do L7 routing, or you could do SSL decryption, or you could do make it an application firewall, defend against DDoS, defend against all the nasty XSS and cross-site scripting attacks and so on and so forth. Or you could do all three with one appliance. And so my job was to make the appliance, which was very popular on premises, adapt to the cloud. And when I got to the networking team, it was already in the cloud. And you could buy on the Amazon Marketplace, you could buy what's so-called VPX, which is the virtual form factor. And then you could use it just like you could use it on the on-prem infrastructure. So it was more designed to be a lift and shift experience, that you were familiar with the Netscaler with on-prem, and you knew how to click on the GUI or use the CLI or do the normal operational things that you do with the Netscaler, and that was replicated in the cloud. And that was not cloud native though, right? Because in cloud native you're more used to APIs, you're used to cattles versus pets. You want to be elastic. And the cloud is not as reliable, right? So your instances go down, and you want to be able to get high availability there. So when you deployed the VPX in AWS, it would look like this: that you picked an availability zone, and then you deployed your VPX in it, and then the traffic would come in through the elastic IP, and then you would send traffic to your backend instances. So very regular load balancer infrastructure or architecture, which was replicated from your data center architecture. But if you wanted to be more cloud native, for instance, if you wanted to spin up more front-end VPXs as the load on the application grew, this was not possible. And one of the reasons was that every time you spun up a new VPX, somebody had to go in with the GUI or a CLI, configure the VPX, and so that it's ready to receive traffic. So some of the goals that I had when I started to design this project was it needed to be cloud native, and then each VPX had to be treated like cattle. So if you shoot one in the head, there was just 100 more you could draw upon, right? And so To do that, you need it to be stateless, so that you store the configuration somewhere outside the VPX. And as the backend instances are scaled, you wanted to reconfigure the VPXs without somebody going into the GUI to reconfigure them. You wanted to pay as you go, so normal scalar architecture in the cloud. And then, just like your application logs and metrics are available in CloudWatch, your NetScaler metrics and logs should be available in CloudWatch and S3. And so I talked about this challenge before. It's a finely tuned machine. So if you, even if you introduce a nanosecond of delay, somebody catches that and asks you, why did you introduce that nanosecond of delay? And so it's non-trivial to introduce a new feature into this appliance. And that's for good reason, right? So our customers are relying on us to give that kind of performance. And with me tinkering around just to make it cloud native, I was not going to ruin our customers' experience. The second problem was that it was the solution to that was, well, let's control it from outside, use the REST API that it had in order to control the machine. But the problem with there is that it's a very imperative style. So if you wanted to configure it, it was probably a 20-step process. And so if step 10 failed, then what do you do? Do you roll back? Do you continue? Do you retry? So there's a lot of orchestration involved there. So a little bit of background on Terraform. Terraform is this product from HashiCorp. It's an open source product. And people use it to orchestrate their multi-cloud infrastructure. And the neat thing about it is that just like Amazon API is also imperative that you need to, let's say if you wanted to create 10 virtual machines, a load balancer, and security groups, you still have to make those API calls in sequence in the right order. So with Terraform, you can declare the desired state, and then it reads the state from the infrastructure, and then figures out what are the changes it needs to make in the right order with the maximum parallelism in order to make those changes. So very neat tool, very popular among DevOps practitioners. And the important thing is that it's designed to be a single user. So it assumes that one user is making those changes. And so it records those changes in a flat file called a state file. And so we decided to adopt Terraform to do this more declarative style, the desired state style of configuration. And so we wrote a Terraform driver to control the NetScaler using the REST API. And so with that, now the NetScaler configuration is now versioned. It can be, we can parameterize it. And you can find those two tools that we developed. First, we had to develop a Go language SDK for NetScaler, and then we developed the Terraform provider. And both are open sourced. And you can find those on those GitHub repositories there. So as I said, the Terraform workflow is like you write this Terraform file in a so-called HCL or HashiCorp configuration language. You execute Terraform plan. It gives you a plan about what, it reads the state file, it figures out what it's going to change in the infrastructure, and then you can ask it to execute that plan. And then it executes the set of REST API calls in order to make that change. And as it's making those changes, it writes those changes into the state file. So the next time you run it, it knows what the delta is going to be from your HCL file. But the key is that it assumes that there is a single state file. It doesn't perform any kind of locking. So if you have multiple developers, for instance, trying to write to the same state file, you're going to corrupt it. So to build our orchestrator to make it cloud native, to give that cloud native experience for the VPX. So we have multiple NetScaler VPXs, maybe in an Autoscale group, and they're trying to send traffic to the backend application instances. And so the control plane or the orchestrator that we wanted to build, something like this. So a DevOps person would send a declarative configuration in HCL, or there would be an instance autoscaling event from AWS from the backend. Or the VPX itself was autoscaled due to some reason, and then the control plane had to react to these events, and then make the required changes using the REST API on the NetScaler VPX instances. So it looks fairly simple, To double click a little bit more into this, the orchestrator needed to observe these VPX related events and invoke these REST API calls. And typically when you build an orchestrator, that means you have a server. And once you have a server, you have to have it, make it highly available. Somebody has to patch it, somebody has to maintain it. And then you need to store the state somewhere, and that's typically database, Postgres, or MySQL. So I built these before with Apache Cloud Stack, non-trivial task. And then we also needed to do things like send metrics to CloudWatch, send the logs to S3. And the solution that we adopted, used serverless for some of the, instead of using a server, we used S3 to store the state. We used serverless function, a Lambda function to get the metrics from the VPX and send it to CloudWatch. And we used Athena to analyze the structured logs from the VPXs. So these are some of the Lambda functions that we came up with. There's a lifecycle Lambda function. It just it reacts to whenever VPX is provisioned. It brings it into service, and if a VPX dies, then there's still customer connections going through it, so it kind of delays the death of the VPX. There's an Autoscale Lambda function which reacts to the web server instances autoscaling and reconfigures the VPX. There's the stats Lambda which pulls the stats using REST API. And there's a weblog Lambda, and its only job is to pull logs from the VPXs. I'll just double click into one of the more interesting Lambda functions here. And this was the Autoscale Lambda function. And so the way it works is that, let's say this DevOps person makes a configuration change, and so sends the new config into an S3 bucket. So that triggers a change event into the Lambda function. And the Lambda function, when it's bundled along with the Terraform binary. And that's something that Amazon lets you do, that it lets you execute these external processes as long as it's a Linux binary. Once you do that, the Lambda function fetches the configuration from the bucket, writes it to the local ephemeral disk of the Lambda function. It reads the current state, which is another S3 bucket. It has to acquire a lock. Remember, I said that it's a single writer kind of scheme here. And then it calls the Terraform binary to apply the state, or apply the delta state to the VPX instances. And then because Terraform writes the state to the local file system, which is ephemeral, it has to save that state back into the S3 bucket. And then it releases the lock. And the same thing, you could see that if there was an auto-scaling event, it would go through the exact same procedure. So the interesting thing with Terraform is that, or with Lambda, is that you can bundle any binary, any Linux binary, along with the Lambda function. And then you can use either like Python os.exec to execute that binary. But the tricky part is that you only have a very ephemeral file system, because the next time your Lambda function executes, the file system may or may not be available. So you've got to be very careful to save that state somewhere durable like S3. And that's what the Lambda function does for that. The second thing we had to invent was the mutual exclusion. Now, let's say there's an autoscale event, and Amazon autoscaling changes the number of instances by 2. You probably get 2 or 3 different autoscale events all at the same time, or very close to each other. And that can lead to multiple Lambda functions running at the same time. And they're all trying to write to the same state file. So you need some kind of mutual exclusion. And to do that, we used Amazon DynamoDB. You just provision a very small write capacity table, and you can use DynamoDB's conditional write feature to do a atomic compare and swap, and that gives you a pretty good mutual exclusion. And if you wanted to use that, that's been open source too at this GitHub repository. So I talked about a couple of other autoscale and a couple of other Lambda functions. There's the lifecycle Lambda function, and so when a VPX comes up, it needs to be plumbed into the VPC. It needs to be you need to manipulate Route 53. You need to manipulate elastic IPs. So all small tasks, but very easy for Lambda to do. Then the stats Lambda is, again, the stats are available through a REST API, they're more useful in CloudWatch, especially if you want Autoscale to react to the metrics from the VPX. So the problem was that the solution with 4 lambdas, S3 buckets, DynamoDB tables, you had to provision VPC endpoints and IAM roles, were very complex to deploy. And so if you look at it, if you had in 2 zones, for instance, somebody had to deploy the backend instances, autoscale the VPXs, and then a whole bunch of surrounding infrastructure with Lambda, IAM, CloudWatch, DynamoDB, and so on and so forth. So pretty complicated to deploy. And on top of that, you had to manage the elastic IPs and Route 53 as well. So the obvious solution was, of course, let's use Terraform to actually deploy the solution as well, and that turned out to be surprisingly good. And so it was so good that you could just do it in a single line with a few input variables. So if you did this, then the entire solution would be deployed, and then you would automatically have a cloud-native VPX, auto-scaling up and down as the traffic went up and down. And so if you looked at CloudWatch, you would see something like this. So this was just an experiment where I ramped up the traffic and then ramped it down again. And you can see that it created or spun up more VPXs to handle the load. And then as the load went down, it was killing those VPXs as well. And the neat thing is that now the metrics are available in CloudWatch, and you get these nice dashboards as well. Then the stretch goal was to get the web access logs from the VPX. Not terribly important, but since ELB, which is the competitor to VPX, had them, I decided to see what it would take to get the web access logs out of the VPX as well. And that was a little tricky because, again, because it's designed as a high-performance machine, the web logs can only be pulled. You can't actually send the logs from the VPX. And to pull the logs, again, it had its own custom format, custom client. So then I had to write this new Lambda function, which would manage this fleet of Ubuntu instances, whose only job was to pull logs from the VPXs and then send them to S3. But again, that wasn't too hard at all, and that got pretty successful. And so the way it works like this, so once a VPX is spun up, also the Lambda function observes that, creates a new Ubuntu instance, and starts fetching logs from the VPX, and then sends the compressed log files to S3. And once it's there, you can use Amazon Athena, which is another serverless big data infrastructure, to query those logs. And so it looks something like this. You create a DDL table using Hive DDL on your S3 schema. These logs are very structured, so it's very easy to define that DDL. And then you can immediately, within seconds, actually start querying weeks and weeks and weeks of logs without provisioning any Hadoop infrastructure, without provisioning any Hive or Spark or any of that heavy stuff. And then you can tear it down when you don't need it. So some of the takeaways is that this was a new experience for me. I mean, I'd built orchestrators before, but that was using traditional Java, MySQL, PostgreSQL, and what I did with this was about 1,500 lines of Python code. It could probably be less if I'd not done such a great deal of logging. But it just shows you that you can build very sophisticated tools and orchestrators with Lambda. But you need to be a little bit inventive. You need to be aware that you can bundle binaries like Terraform along with your Lambda functions. You may need need to build additional infrastructure like DynamoDB mutexes. But then once you get the hang of it, you just find more opportunities. Like, hey, this is an event-driven workflow, so maybe I can use Lambda to do that too. And then, it just the whole serverless ecosystem, including Athena, just makes it a wonderful and easy experience that even a single developer can build this sophisticated infrastructure. Some of the bad things were, of course, it was hard to debug failures, so the solution, I guess serverless as a better solution was mostly just more and more logging. And but even then it was harder to correlate, because if you had 100 Lambda functions running, you wouldn't know where necessarily the failure was. So it was a lot of clicking and debugging there. If you're doing any state mutation, it has to finish within that deadline, which the Lambda function has, which typically I think it's a maximum of 5 minutes. So in our case, it was good enough. But if you're doing any kind of other kind of orchestration where you needed more than 5 minutes, then I think the state management becomes considerably more complex. But again, here I think the Terraform itself was pretty robust in its ability to recover from a failed run, and so even when the deadline ran out, Terraform was able to recover from that failure. And the whole solution is it looks like a lot of baling wire and gum, and but again, if you use a tool like Terraform or CloudFormation, it gets much easier to deploy and manage. Last but not least, and this was the most important takeaway for me, is that my colleagues saw this and they said, "Hey, what? We thought this was going to be a 6-month or 8-month effort," and in fact, they are building a similar effort as part of a bigger product. And but they saw the end result; it worked, but they didn't understand it, because everybody is still used to that traditional orchestrator experience. They want the dashboard, they want that GUI, they want the login experience, and so it was a hard sell. But there's customers waiting still for the main product to catch up with this cloud native experience. In the meantime, they're using this. And again, not all of them are used to this. Some of them haven't heard of Lambda. So it's a tough sell for them also. So the unfamiliar architecture, so the choice of Terraform, the choice of Lambda, was not for everybody. So I think that's a useful lesson for any engineering project, that you have to take in the context of where you want to deploy the solution. So if you want to take a look at the code, there's that GitHub repository there. If you got any feedback from me, feel free to tweet me at Chiradeep. Thank you. It's a little hard. So as I said, we're building the similar experience on a as a service product, and that's going to be at least 3 to 4 engineers for 4 to 5 months. This took me about 4 weeks to develop, just me alone, because again, you're not maintaining infrastructure like Hadoop. You're not maintaining infrastructure like servers. The main way is to invoke it from the command line, send it different sets of events, and then see how it reacts. But the logic is not too convoluted. The corner cases are the tough ones, and that's very hard to test. Mainly, what happens if the deadline fires? What happens if there's a state file corruption? Those are very hard to test.
All right, thank you so much, Chiradeep. That was cool.
Thank you.